Okay, this is the notes for section 8.1, geometric mean for geometry students on Tuesday, 3/28, 2017. And so if you have not yet gotten the handouts for this section, if you're not in the band and choir, so just a reminder, band and choir students can be working on their own independently ahead on the work that they have to get ready, or they can listen to this lesson as well. And then the students who are not on the band and choir trip should get the handouts that they need if they didn't get them previously, and then we'll move on with this lesson. Also, band and choir students should just be working by themselves, not with anyone else, and they should not be talking. If they'd like to sit isolated in the back row, that would be fine as well. So this section is 8-1 on the geometric mean, and the essential question today is, can you find the geometric mean and solve problems involving right triangles? If needed, you can pause this so that students can get written down what they need to write down for this section, and I will just kind of move ahead. So if you need to pause it or just back it up a little bit, just do that as needed. The handouts, just to kind of let you know, everybody should have one handout that looks kind of like this. And those are small handouts, and I do have some extras, so if you need to kind of find that, take an extra one, that's fine. The other handout should have this at the top that says geometric mean, and it goes below. It also has some fill in the blanks that we'll do kind of as class goes on here. And then the third page handout that you should have is the one that looks like this. And this is two of those, and that is for the kind of lesson notes as we go. So again, let me go back to this first slide, and you should be writing your essential question and your heading for this. Now I'm going to move on from this slide. So again, if you have to pause that, go ahead and do so. And in this section, we're going to have a very, very large key terms page. And we're going to actually put a big review on that key terms page. So if you do need extra space, kind of just go to the next odd page after this. And so I'll just pass that little part. And this is the key terms. The first thing that you're going to write here is and I'll just get a different marker here. The first thing that you're going to is write about the geometric mean. So the geometric mean happens when the means of a proportion are the same number, then that number is called the geometric mean of the extremes. So the geometric mean, another important thing to write down is that the geometric mean between two numbers is the positive square root of their product. And so then you can write this as well. And then just below that, we'll kind of write what that means also. And we've already talked about the extremes and the means as we've gone through things earlier. So this is your key terms on that odd page. Now I do have this big review that goes in your key terms set up already, and so I have a lot of the work done there. So I will be giving you a little bit of time, or you can pause this as you need to. Notice in this proportion that you just wrote that if I cross multiply, I get x squared equals AB. So x equals, and it is the positive square root of their product, so it's just the square root of AB. And since I think we had in chapter 7 a couple problems like this, but now in this chapter, we're going to start out with a section about geometric means. And since we have the square root of a number, we're going to review. And so you're going to write this as a heading, review of simple radical form. So the first thing I'd like you to do is take a moment and just make this table that has x values and x squared values. I'd like you to write from 1 to 12. So in the x column, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And then in the x squared column, just the answer when you square each of those. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100, 11 squared is 121, and 12 squared is 144. Now, when you use simple radical form and maybe have done this in the past, you've maybe brought things down to their prime factorization. In this case, we're generally just going to take the numbers that we have and divide by perfect square factors. So the ones that I'm circling right now will be what we're going to divide into numbers. And, you know, I can keep going as we look at that. And we want to try to find the biggest perfect square factor that something has. And I'm going to get rid of some of this yellow just so that it's not there at the end when you're done with these notes. So maybe I'll also get rid of some of this other stuff. Oops. There we go. And so then I'm just going to go through the rest of this handout with you. I'll leave that kind of near the top so that you can see that. I'll just be explaining what some of these things mean. And so I will trace over some things and then I will get rid of that. So SRF is just what I write on your tests and quizzes to mean simple radical form. And so if I'm taking a little bit of points off because you didn't have something in simple radical form, that's what SRF means. And you've learned about this earlier, but I'll just remind you. Simple radical form means that when you have that radical, there are no perfect square factors under that radical sign. So then I have something that's okay and not okay. The square root of 6 is okay because it doesn't have a perfect square factor up on this table. But the square root of 12 is not okay because 4 will go into that 12. So it's not in simple radical form for that part. So one big thing, and this should be review for you, one big thing is that we can't have a perfect square factor under the radical. And so maybe write yourself that little note as well. Then the second thing that's over, you know, this side is if we have a fraction, anything on the top but a radical in the bottom, that's what is not allowed. There is no square root sign allowed in the bottom, which is also called the denominator of the fraction. So give yourself a little note about that. So if I have this one, the square root of 6 over 4, write that down, that is okay. But 4, if I flipped it upside down, 4 over the square root of 6 is not okay, because I can't have that square root in the bottom of my fraction or in the denominator of the fraction. So then we'll just kind of do some little review problems right in here so that you have those in your notes. And again, if you need to pause it, just go ahead. So my problem that's labeled as number 1 is the square root of 25. And since the square root of 25 is a perfect square, the square root of 25 is equal to plain old 5. So if it's a problem like that, then we can just say the square root of 25 is equal to 5. And then notice my next problem, number 2, is the square root of 50. So 25 is the perfect square, and it divides evenly into 50. So I'm going to change that 50 into a 25 times 2. And the way that I'm going to do that is I'm going to rewrite this as the square root of the square root of 50. I'm going to rewrite as the square root of 25 times 2 under the radical. And then I'm just going to rewrite that as two square root problems kind of next to each other. So the square root of 25 times the square root of 2. And since that square root of 25 is a perfect square equal to 5, then my answer here will be 5 the square root of 2. And so then that is the answer in simple radical form. And we will be expecting ourselves to get answers in simple radical form. You'll notice for this next one, number 3, which is the square root of 112, I did it two ways. Sometimes if I just show you one way and you don't approach it that way or notice what I am going to tell you, then it gets a little hard for you to find the answer. So take your calculator right now and take 112 and divide it by 4 and see if it divides evenly. And then also keep dividing it by some of these other numbers. Divide it by 9, divide it by 16, divide it by 25, and just kind of see what is the biggest. We want to find the biggest perfect square factor. The biggest perfect square factor of 112. Now I'm going to tell you what that should have been. You should have found that 16 is the biggest perfect square factor. So let me get rid of some of this yellow again. So 112 can be rewritten as the square root of 16, and if you take 112 divided by 16, it goes 7 times. So 16 times 7. And this one's just like number 2 if I approach it this way. So the square root of 16 times the square root of 7 is 4 the square root of 7. And again, this should be all kind of review for you. Well, if you notice when I asked you to divide these numbers that are perfect square factors from for this number 3 a second time, and I will ask that you write it twice. If I divide and I notice that 4 goes into 112 right away, I might use that one. It's a perfect square factor of 112. It's not the biggest perfect square factor. So that just means we have to do a little bit more work as we go. So if I did use the 4, I would have gotten the square root of 4 times 28. And so then that is the square root of 4 times the square root of 28. And the square root of 4 is 2, because the square root of 4 is equal to 2. That's a perfect square factor. So then I can make that into 2 the square root of 28. Now, that's not the same as the answer I got a minute ago because 28 still has a perfect square factor. So we kind of have to go back up over here and, oops, all the way to the 4 and see if 4 goes into 28, which we know it does go 7 times. And so the way we're going to handle that is we're going to rewrite this as 2 on the outside, the square root of, we're going to change that 28 into 4 times 7. And so that'll be 2 the square root of 4 times the square root of 4 times the square root of 7. And then the 2 just stays 2. The square root of 4 now turns into 2 again, a plain 2, and then we'll just multiply that by the square root of 7. And then the outside 2 times 2 is equal to 4. Just a reminder, when you're working with radicals, if they have things that are multiplied that are outside of the radical and things that are inside the radical, you can multiply things outside of the radical with other things outside of the radical, things inside the radical with other things inside the radical. So this turns out to be 4 the square root of 7, and you should notice that That's the same answer that we got. The thing to be careful of is not to stop right there where we had the square root of 28, because that's not all the way in simple radical form. So just be careful of that as you go. Now, the next problem, and I won't be able to see my perfect squares as well after I move on here. If you do run out of space on this key terms page, by all means, you can go to the next odd page, because these notes are just starting for this section, and then you'll have plenty of room. Because I have 6 things labeled here, but I will be adding a little bit more in addition to that as we go. So this next problem, number 4 here, and I'd like you to take a moment and write that. So this is number 4. Just take a moment and write that. 4, the square root of 24 over 2 the square root of 3. Now I'm going to kind of just talk about 2 ways to do this one as well. And I will just tell you that right now, because there's a square root of 24 and a square root of 3, since those are both under the radical symbol, I can reduce those out. And I'm going to take maybe a little more steps than I would when I'm just kind of trying to simplify a problem, but we're remembering how to do some things as we go here. So I'm going to rewrite that square root of 24. It has a perfect square, oh, not a perfect square factor. It has a factor of 3, and we want to be able to cancel it with that 3 on the bottom. So I'm just going to rewrite this as the square root of 8 times 3 over 2 the square root of 3. And then this is the square root of 8 times the square root of 3 over 2 times the square root of 3. And then when I do it that way, I can cancel these 2 square roots of 3, and I can get then the square root of 8 over 2. Now, that is not simplified yet, but that's what I kind of get at that point. So you maybe are noticing I could have just reduced this 24 and 3 and gotten that 8. And then this 2 is just still down there where it was. So take a minute and write that. Then we need to put this in simple radical form still. And so 8 has a perfect square factor of 4. 4 goes into 8 evenly. So I'm going to rewrite this as the square root of 4 times 2 over plane 2. Now, one thing I want to point out is I can't cancel this 2 that's under the square root with this 2 that's outside of the square root. So I can manipulate things inside the radical or square root symbol with things inside and things outside with things outside, but I can't kind of cross over. So then I'm just going to rewrite this as the square root of 4 times the square root of 2 over plane 2. And now that square root of 4 right here, that is equal to plane 2 outside of the radical. So my next step is just to write that as 2 the square root of 2 over 2. Now I have two number 2's outside of the radical. One is in the numerator or top, one is in the denominator or the bottom. So I can say 2 divided by 2 is 1. 2 divided by 2 is 1, and I get for my final answer just plain old the square root of 2 over 1, which we can write as the square root of 2. I put my number 5 kind of up over here, so take a minute and write number 5 as 1 over the square root of 3. So for this one, my problem is that I have the square root in the bottom of the fraction, and I'm not allowed to just leave that square root of 3 on that bottom of the fraction. So that's what I have to take care of. I'm just going to remind you, because you've probably done this before, or you should have done this at some point. In order to rationalize the denominator, that's really what this is called, we're going to take this denominator, which is the bottom of the fraction, which is the square root of 3 in this case, and we're going to multiply it by itself. But so that we don't change the value of the fraction, when I multiply this bottom by the square root of 3, because that'll make it the square root of 9, and that's a perfect square, so it'll be back to plain old 3. In order not to change the value of the fraction, I multiply by the square root of 3 over the square root of 3. Just a reminder this fraction, the square root of 3 over the square root of 3, is equal to 1. So we're not changing the value of the problem. We're just multiplying by 1 in a different form so that we can kind of simplify this. And so this is 1 times the square root of 3, which is the square root of 3. And then the square root of 3 times the square root of 3 is the square root of 9. And then I'll just go below a little bit here. That square root of 3 just stays the square root of 3 on top, but the square root of 9 is a perfect square, so the square root of 9 is plain old 3. And so that is the simple radical form. For 1 over the square root of 3 turns out to be the square root of 3 over 3. And there's a relationship there that's kind of easy to follow. You're going to find if I have 1 over the square root of 2, I can rewrite that as the square root of 2 over 2. If I have 1 over the square root of 5, I could write that as the square root of 5 over 5. So just some things to kind of think about. Then the next problem, this number 6, if you'll write that one down, it should say, it's a little bit hard to see, but it should just be the square root of 5 over the square root of 3 times the square root of 3 over the square root of 6. So take a minute and you can write that down. I'll get rid of my yellow there. Now for this one, I can handle things under the radical with other things under the radical. These are multiplied together, so I can reduce things that are in the top or numerator of either one of these fractions with something in the bottom or denominator of either one of these. And I'm going to notice that there's a square root of 3 up here, and there's a square root of 3 down there. So I'm going to divide them each by the square root of 3 and be left with 1. So let me write that in a color that I'll leave there. So these cancel to be 1 and 1. So then that means that this problem is when I multiply kind of straight across, square root of 5 times 1 is the square root of 5, and 1 times the square root of 6 is the square root of 6. Now that would be my answer, but it's not in simple radical form. So to make it in simple radical form, I have to multiply by whatever that radical is in the denominator, which in this case is the square root of 6. So I have to multiply this denominator by itself, which is the square root of 6. And then to not change the value of the fraction, I have to multiply by the square root of 6 over the square root of 6, because that's equal to 1. So let me kind of get rid of that again. And now I'll just write that in. So I'm purposefully choosing to multiply by the square root of 6 on the bottom, whoops, which I did not write, the square root of 6 on the bottom. And then to not change the value of the fraction, I multiply by the square root of 6 on the top as well. And then I'm just going to multiply straight across. So the square root of 5 on the top times the square root of 6 is the square root of 30, and then the square root of 6 times the square root of 6 is the square root of 36. So when I do that multiplying, let me choose a different color here. When I do that multiplying, I'm going to get the square root of 30 over the square root of 36, and that is equal to the square root of 30. I want to think to myself, is there a perfect square factor that goes into that? And since I'm kind of thinking that over, I'm just going to slide way up here, and I'm asking myself, does 4 go into 30? No. Does 9 go into 30? No. Does 16 go into 30? No. Does 25 go into 30? No. 36 is over that, but 36 is a perfect square for our denominator or bottom of the fraction. So then when I go back here, that square root of 30 just stays the square root of 30, and the square root of 36 becomes plain old 6. Now, for the next part here, I have just some more problems that I want to kind of write down with you. And so I'll just kind of draw a line there. If you've filled up or want to leave room for questions for this section, you can go to the next odd page and just kind of write that this is the review continued. I'll just go on this slide, continued. And if you are just going down, then you sure can do that. I have a few more problems that I just want to go over. So I'm calling these problems A. So for letter A, it's the square root of 300 to simplify. And I'm going to write that a little bit better. The square root of 300. And so for this one, I want the biggest perfect square factor that goes into 300. That would be 100. So that is equal to the square root of 100 times 3. And so then I'm going to separate those two radicals, the square root of 100 times the square root of 3. And then the square root of 100 is plain 10. So we get 10 the square root of 3. If I were here, I'd be having you maybe do these on your own, but I'm just going to kind of run through them as another example problem for us to do. The next one is the square root of 6 over the square root of 3 times the square root of 18 over the square root of 3. Now, on this one, I can do some reducing kind of as I go. Everything here is under a radical sign, so I can reduce any numerator with any denominator. And so I'm going to say that the square root of 3 goes into the square root of 18. The square root of 6 would be left over when I do that division. And if I take the square root of 3 divided by the square root of 3, I get 1. If I take the square root of 6 divided by the square root of 3, I get the square root of 2. And so when I do that, I'll just do it in a different color so that I can kind of leave it there. So I'm going to say the square root of 3 divided by the square root of 3 is 1. The square root of 18 divided by the square root of 3 is the square root of 6. And then in the first fraction, the square root of 3 divided by the square root of 3 is 1. And the square root of 6 divided by the square root of 3 is the square root of 2. Now when I just multiply straight across, I get the square root of 2 times the square root of 6 on the top, which is the square root of 12. And 1 times 1, which is just 1. So I can either write the square root of 12 over 1, or I can just write it as the square root of 12. And then that's equal to a perfect square factor of 12 is 4, so that's equal to the square root of 4 times 3. And I'm just going to write that because I don't like the big dot. The square root of 4 times 3. And this is the square root of 4 times the square root of 3. So this is 2 the square root of 3. Two more problems that I just want to remind us of, and that is the Pythagorean theorem and kind of the FOIL method. So we've kind of reviewed these earlier this year, but we're going to use them in this section. So the first one is the Pythagorean theorem, and if I have a right triangle here and this leg on the left is 7, the bottom leg is x, and 19 is the hypotenuse. So I'm going to actually label that. And if you remember, if I trace the right angle, I didn't trace the hypotenuse. So I'm going to write HYP because we'll need to know that in this chapter. So if you remember, for the Pythagorean theorem, a squared plus b squared equals c squared. So in this one, it's x squared plus 7 squared equals 19 squared. I'm actually going to leave those without squaring them and just remind myself if I wanted to get x squared alone, that means x squared equals, I'll subtract 7 squared from each side, 19 squared minus 7 squared, and then to get x by itself without the squared, I'll square root each side, and so maybe I'll just write that in yellow for a moment. When I square root each side, the square root of x squared is just plain x, and Then on the right-hand side, we'll have the square root of 19 squared minus 7 squared. And now, since we just put things in simple radical form, that's what we're going to do in this problem. So x equals, when I square these, it'll be the square root of 361 minus 49. So x equals the square root of 312. And then I'll kind of just go up over here. And so then x is the square root of 312. And I want the biggest perfect square that goes into that. Well, I'm going to notice that 4 goes into that, so I'm just going to start with that. 4, and 4 goes into 312 78 times, so 4 times 78. And then that is x equals the square root of 4 times the square root of 78. And so x equals 2 the square root of 78. And then I'll try some other perfect square factors for 78. None of them are going to go in there. And actually, in my own work and own head, I just took 78 and started dividing by things I knew that went into it. So 2 goes into that. That would be 3 and 9, and then 3 will go into that, and that is 1, 3. So for 78, the prime factorization is 2 times 3 times 13, and those that means there are no other perfect square factors. So I can kind of leave that like that. The next problem that I want to do is I'll number it as number 8, and that's a reminder of the FOIL method. First, outside, inside, and last when we multiply two binomials times each other. So x plus 3 in parentheses times x minus 5 in parentheses. So just a reminder of how we do that, and I'll kind of go through it step by step. The first terms are right there, x times x. X times x is x squared. The outside terms are x times negative 5, and that minus 5 can be thought of as plus negative 5, and that'll be x squared minus 5x. And then the inside terms here will be 3 times x, so positive or plus 3x. And then the last terms are the 3 and the negative 5. 3 times negative 5 is minus 15. So that's kind of thinking that through. Now I'm just going to write it in a color to kind of leave there. And I think one more. There we go. So first terms again are x squared. Outside terms are minus 5x. Inside terms are plus 3x. Last terms are minus 15 when we multiply. Notice here we can combine like terms, and so we'll do that next. And when we do that, we'll get x squared, and then minus 5x plus 3x is minus 2x, and then minus 15. Just a little reminder of the FOIL method. Here's one more. I don't know, I called it C, I'm not sure why. Y minus 6 times y minus 2. And just kind of think about that. First terms, y times y is y squared. Outside terms are minus 2y. Inside terms, minus 6y. Last terms, plus 12. And then combining like terms, y squared minus 8y plus 12. If you need to pause and write anything down from there, you certainly can. This has taken a little bit, so I'm going to have you go next to the handout that has some kind of fill in the blank things. I have things highlighted on here, and so I'll just ask that you take some time and highlight things. The geometric mean, we already talked about that a little bit. The geometric mean of two positive numbers, a and b, is the number x, such that a over x is equal to x over b. So x squared equals ab, and x equals the square root of ab. So then this example, the geometric mean of a equals 9 and b equals 4 is 6, because you just take the square root of 9 times 4. The next one, so you should have underlined some things there. The next one, I pretty much underlined that whole theorem. If an altitude is drawn to the hypotenuse of a right triangle, so if you look at this, here's the big right triangle they're talking about, and this is the altitude that's being drawn in. So if the altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed, that means this triangle over here on the left and that triangle on the right, are similar to the original triangle and to each other. So if we're going to name those, and I call them like long leg, short leg, and hypotenuse, and I'll just start with one of these triangles, and they use triangle ABC. So triangle ABC is the big right triangle. If I name that as ABC, I'm using the hypotenuse and the short leg. So triangle ABC is similar to. And then on the left triangle, I'll use the hypotenuse and the short leg also. So that would be triangle ACD. Triangle ACD. And then if I use this little right triangle on the side, then hypotenuse and short leg, it would be triangle, is similar to triangle CBD. So you might want to write that down as well. Now I'm going to write these fill in the blanks. If you have, if you don't get that done, I will put that up at the beginning of the hour tomorrow when I'm back. So this one says that x over h equals h over y. And this is the geometric mean altitude theorem. And when we cross multiply, we're going to get h squared equals xy. So what we're going to write on here is that h equals the square root of xy. And so h is this altitude right here, and it's equal to the square root of these two pieces that are right here, x and y. And then the next one is the geometric mean leg theorem. And over here, we get that b squared is going to be xc and a squared is going to be yc. So I'm just going to take a minute and write what those are. So this one is going to be b equals the square root of xc, and a equals the square root of yc. And we'll go over that a little bit more tomorrow. So I will see you tomorrow. You should have written homework A and homework 1, and they are both due on Thursday for the people who will be here and not going on the band and choir trip. And actually the band and choir people, it's due also. They'll have another thing due and they'll take a quiz.